Right, so today we're going over position, velocity, and acceleration. So these are some few things to know involving some equations. So in order to find the final position of an object, you would take the initial position and then add it to the area under the graph of the velocity graph from the interval of time initial to time final. What this would give you is basically delta S, which is the change in position. You would add it to the initial position and it would give you the final position. And now we would go on to acceleration. So acceleration of any interval would basically be velocity final minus velocity initial divided by delta t, which is the time interval. And then average velocity is essentially the same thing, delta v, which is velocity final minus velocity initial, over delta t, which is also known as the rate of change of velocity. And now another way to find the final position is SF is equal to initial position plus initial velocity times delta t plus 1/2 of acceleration and times delta t squared. And both of these will be useful, and as well as finding out the final velocity. To do that, you would basically plug it into this equation down here, which is final velocity squared is equal to initial velocity squared plus 2 times acceleration times delta s. Delta s meaning the delta position, the change in position over the interval. So these are some equations that are going to be really important for the first few steps of calculus related questions in physics. So I'd suggest to write them down. All right, so first let's look at number 5. So number 5 is this figure shows the position graph of a particle. Draw the particle's velocity graph for the interval of 0 to 4 seconds. So let's first draw a graph right here. We have 1, 2, 3, 4, and then 0 over here. So this is our position graph. If you remember, in order for a position graph to go to a velocity graph, you would have to differentiate it. Rather, the slope of a position graph is going to be your velocity at a given moment. And we can take these velocities through intervals and then plot them. So let's take these three intervals right here. So 0 to 1 is going to be our first interval. So from 0 to 1, we see that the graph is decreasing. And to find how much it is decreasing, let's first get the average velocity, in which we'd use the equation. So we have velocity average is equal to delta s, or delta position, which is going to be 10 minus 20, and then divided by delta t, which is 1 minus 0, 1 minus 0. And then we would have negative 10 over 1, which gives us a velocity average of negative 10 meters per second. And so from the interval of 0 to 1, our average velocity is negative 10. So let's say 10 is right here. And then let's say negative 10 is right here. So this would be our velocity line, or rather we could write it in a different color. We could do dark red. So that would be our velocity line from 0 to 1. And now let's find the average velocity from the interval of 1 to 3. So from 1 to 3, we don't really have to do any calculations, since we see that there's a straight line, the position graph, which means that the object isn't moving in that interval, which also means that the velocity is equal to 0. So from the interval of 1 to 3, our velocity would be just 0. So our graph would jump here. And the reason why there's a breaking point in here is because our velocity isn't gradually changing. It's rather like having a sharp change in velocity. So our velocity graph is going to be like discontinuous, or a piecewise function rather. And now let's find the average velocity between 3 and 4. So let's use the average velocity equation. So we're going to have delta S, which is going to be 0 minus 10, and then over 4 minus 3, which is delta t. And we're going to have negative 10 over 1. So our velocity average from interval 3 to 4 is also going to be negative 10. in which our velocity graph from 3 to 4 is going to be plotted at -10 right there. So this would be our velocity versus time graph from interval 0 to 4 seconds. And does this particle have a turning point or turning points? We do know that our particle does stop moving from time interval 1 to 3, and then it starts moving backwards again. It doesn't exactly start moving in the opposite direction, but it does stop and go. All right, so let's take a look at number 8. So number 8 is this figure is somewhat idealized graph of the velocity of blood in a ascending aorta. I don't even want to pronounce that, but during one beat of the heart. Approximately how far in centimeters does the blood move during one beat? First, we have to remember that at the end of this question, we're going to have to change our meters to centimeters. So we're going to just square that in. But how do we find the how much the blood moves during one beat given the velocity function? How much the blood moves during one beat is going to be delta S. And if you remember, delta S is going to be the area under the graph of the velocity function. So we want to find the area under the graph between this interval right here from 0 to 0.4 and especially 0.1 to 0.3. How could we do that using calculus? So in order to find the area under the graph here, we're going to have to break this up into the triangles in which we can find the area of. So we can't exactly find the area of this triangle right here, but what we could do is break it up into two right triangles. So we would break it up at the halfway point right there. So now let's draw two triangles. So we have one right here, and then a second one right there. And let's find the length. So this is the midpoint, so this would be 0.15. So the base of the first triangle would be 0.05. And then the base of the second triangle would be 0.15 to 0.3, which is 0.15. And then the heights of both the triangles would be 0 to 0.8, so it'd be 0.8. And then the height of this will also be 0.8. And now we just calculate the area of the triangles, which is going to be 0.05 times 0.8 over 2. And then we would also have 0.8 times 0.15 divided by 2. And if you do the calculations, you'll have 0.06 for the first one, 0.06 meters, and the second one you'll have 0.02 meters. And now we just add them together. Add the areas of both triangles, we would have 0.08 meters, which is how much the blood moves during one beat. But we want to find the answer in terms of centimeters, or rather in units of centimeters. So meters, 100 centimeters is equal to 1 meter. So all we need to do is just multiply 0.08 by 100, in which we would have 8 centimeters. So our answer of how much the blood moves during one beat is going to be 8 centimeters, or rather delta S. All right, so let's take a look at number 9. So number 9 is this figure shows a graph or velocity graph of a particle. Draw the particle's acceleration graph for the interval 0 to 4. So we're going to do the same thing we did for the position velocity. The acceleration of the velocity graph would essentially just be the slopes at any given intervals. So let's just draw a little mock graph here. So we have interval from 0 to 4, and then now the y values will be right here. And now let's take a look at the intervals that are going to be most important. So 0 to 2, we have a straight line, and then 2 to 4, we have a straight line. So those are two intervals we're going to be looking at. Now from 0 to 2, we could use the average acceleration equation, in which that's going to be delta v, or rather velocity final minus velocity initial. So velocity final would be at 3, so it would be 3 minus 1, which is velocity initial, and then delta t is going to be 2 minus 0. And our answer is going to be 2 over 2, which is just 1. So average velocity from the interval of 0 to 2 is going to be 1. So we would just draw a straight line at 1 on our graph from to interval 2. So let's draw that in red. And this y value represents 1 right here. And now we look at the interval from 2 to 4. So if we see from 2 to 4, we have another straight line. So a straight line in a velocity graph means that it's not accelerating. The velocity is constant. It's in uniform motion. Uniform motion, that it means that it's not accelerating. So we can only assume that the acceleration is 0 from 2 to 4 without doing any calculations. But let's say you were to do the calculations. Let's plug it in. So we're going to have average velocity is equal to delta v, which is going to be 3 minus 3, divided by delta t, which is going to be 4 minus 2, which is going to give us 0 over 2, which is just 0, which matches up with the fact that it's not accelerating. All right, so for number 6, I want you guys to try this question out, so you can pause the video and try it out. All right, so let's take a look at number 6. In number 6, we have a particle starts from x 0 equals 10 meters. So it starts at a position of 10 meters at t equals 0 seconds and moves with the velocity graph shown in the figure. Does the particle have a turning point, and if so, at one time? So a turning point, what it means is that the velocity is going from negative to positive, or rather it's going in one direction and then it's now moving in different direction. So from the velocity graph itself, we could just tell that the turning point is when it crosses, or when the graph has a 0. In a position graph, how you would find the turning point is at a maximum or minimum of the graph. So turning points would be at the max minimums, which essentially means that the velocity is 0 at that point. And it's going from decreasing to increasing, or decreasing or increasing to decreasing. So our turning point is going to be at t equals 1. And now let's take a look at B. So we have, what is the object's position at t equals 2 seconds and t equals 4 seconds. So we know the original position is 10 meters. And now to find delta S between through these intervals, we have to find the area under the graphs between the intervals. And that'll give us how much the position has changed from 10 meters. So first let's take a look at t equals 2 seconds. So t equals 2 seconds, we want to find the area under this graph. And when you find the area under the graph, you always want to do it relative to the x-axis. So we need to find the areas of both these triangles and add it to 10 meters. So from 0 to 1, the area under the triangle is going to be, basically, if we find delta S, it's going to be this triangle right here. We could draw it out. So our base is going to be 1, and then our height is going to be negative 4. So now we just find the area of a triangle, which is going to be 1 times negative 4 over 2, which is going to be negative 2. And now we have our interval from 0 to 1, which is going to be minus 2 meters. And then now let's find the position change from intervals 1 to 2. That's going to be the same area under the graph of this triangle, which is going to be, we could draw it out. It's going to be base of 1 and then a height of 4, in which we're going to have 1 times 4 over 2, which is just 2. So our position change was also 2 meters there. So we have plus 2 meters. And 2 meters minus 2 meters is going to be 0. So our position at t equals 2 seconds is it's exactly where we started, 10 meters. And now let's take a look at t equals 4 seconds. So for t equals 4 seconds, we want to find the area under the graph of this big triangle right here and that small triangle, and we want to add that to 10 meters. So for the small triangle from 0 to 1, we know from the interval of 0 to 1, delta S is going to be negative 2 meters. So we can just conclude that already. And now we need to find the area under the graph from interval of 1 to 4. So 1 to 4 is going to be, if we draw a triangle, it's going to be, the base is going to be 4 minus 1, which is 3. Then the height is going to be right here, which is going to be 12. And now if we find the area of the triangle, it's going to be 12 times 3 over 2, which is going to be 36 over 2, which is also 18. So delta S from the interval 1 to 4 is 18 meters, so we add 18 meters. And now if you do all of that, simplify all that, we're going to have 26 meters as our final position at t equals 4 seconds. Alright, so I want you guys to try number 10. So for this, you're going to have to find the position, velocity, and acceleration, the instantaneous of at t equals 2 seconds. So you could pause the video and try that out. Alright, so let's take a look at number 10. So number 10, we have this figure shows a velocity graph of a particle moving along the x-axis. Its initial position is x0 equals 2 meters. So we know that it starts at 2 meters. At t equals 2 seconds, what are the particle's position, velocity, and acceleration? So t equals 2 seconds is going to be right here. That's going to be our little important part right here. So first, let's find out the position. So position, we want to find, if you remember, it's the area under the graph of the velocity graph. So we want to find the area under the graph from 0 to 2, the interval. And then we want to add it on to 2 meters. That would give us the position at t equals 2. So to do that, to find the area under the graph, this isn't the exact shape. So what we could do is break it up into two shapes. We could break it up into a triangle and a rectangle in which we could solve for. So let's take a look at the rectangle. So, the triangle, that's a very odd triangle. But so for the triangle, we have a base of 2, and then we have a height of 4. And now we find the area of the triangle, which is 4 times 2 over 2, which is equals to 4 meters. And then we find the area of the rectangle, which is going to be the base is 2, and then our height is also going to be 2, in which 2 times 2 is going to be 4 meters. And now all we need to do is just add that to 2 meters, so plus 4 meters, and 10 meters is going to be our position at t equals 2 seconds. And now we got to find the velocity. So let me first label this. So velocity is going to be basically we don't need to do any calculations because since this is a velocity graph, it gives us the instantaneous velocity at t equals 2 seconds would just be the point. So this would be the velocity at t equals 2 seconds, which if we look at the right y value, it's 2. So our velocity at 2 seconds is going to be 2 meters per second. We could just deduct that from looking at the graph. And now let's take a look at the acceleration. So the acceleration is going to be the slope of the line at t equals 2 seconds. So in order to find the slope here, a numerical value, what we need to do is take the two closest points to it and find delta A. So, or rather, average velocity, or average acceleration actually. So delta V is going to be 0 minus 4. And then delta t is going to be 3 minus 1. So 0 minus 4 is negative 4, and then 3 minus 1 is 2. So our average acceleration is going to be negative 2 meters per second squared. And that kind of checks out, as you could use the slope formula here and see that for every 1 second that is passing, it's slowing down by 2 meters per second. So that is going to be our average velocity at t equals 2 seconds. Alright, so that was basically for position, velocity, and acceleration. Uh, Again, these equations right here are very important to note down as you're going to be using them over the curriculum. And this section was mostly to understand how to see the graphs of velocity, position, and acceleration, as well as how to deduct acceleration from a velocity graph and how to deduct position from a velocity graph and whatnot. So yeah, it's basically it.